Good afternoon. So, welcome to the first colloquium of 2025. Started a bit late in the year. It's a great privilege to have Gavin Salam here. This is a difficult introduction for me to make, but I'll make it. So, Gavin received his PhD from Cambridge in 1996. So I just need to show how old he is. And then I went through Milan, CERN, spent about a decade in Paris at the CNRS in Paris. Had a short partial stint in Princeton, was CERN staff for almost a decade. And since 2018 is in Oxford. Where I'm not going to say what are in Oxford because it's lots of writing. Gavin has received several distinctions. In 2010, a silver medal from the CNRS, was elected fellow of the Nobel Society in 2017, and finally, I hope not finally, but was the recipient of the Dirac Prize by the IOP in 2020. Okay, that's all information. His research has covered a vast number of topics in high energy physics. He has made many important contributions and developed some tools that are workhorses of the LHC program. Most contributions are in jet physics, where one of the proponents of the anti-KT jet freedom that many people have heard about, author of the fast jet code that everybody in particle physics uses nowadays. I will jump through many achievements. So recently, Gavin just concluded an ERC where him and the team around him made what I consider to be two revolutions in one in what concerns the simulation of the gaps in what is called quantum charts. Also contributions to Higgs searches that unfortunately will not have the third channel to find the Higgs. Otherwise, we would probably not be able to do it here out of the commitments, and also some contributions in the realm of the heavy items. So this talk, it's a really good time to have this talk here. We are currently discussing the update of the European Strategy for Particle Physics, which includes proposals and plans to build a next collider, or try to build the next collider. And I think it's very important to ask, why should we do it? And I think that's what we talk, what I hope that we're going to do. Thank you very much.
Thank you for that nice introduction. So this is a slightly unusual colloquium. Normally, people give a colloquium about the research they've done over the past 5-10 years. This is a colloquium about the field of particle physics. Why? Because over the past 10 years, some of you may have watched famous YouTubers to talk about particle physics. There's been a story about particle physics that I think is the wrong story. And so this talk is about what I think is one right story. I think there are many possible stories one can tell about what particle physics is. What it has done, where it's going. This is my take on it. So it's not just about the future, it's also about the present. What we're doing right now, and what we're trying to achieve. So let's take a step. What is particle physics? Particle physics wants to understand the fundamental forces of the universe and the fundamental particles. What are we made of? What else is out there? And how does it hold together? Without the interactions, we're nothing. Now, you'll often see a version of this picture which shows the fundamental particles. And the one that is really going to be central to this talk, in a sense, is the Higgs boson, but only in a sense. When it was discovered in 2012, and you have the video about the discovery in the Leaf office in the entrance to the building, many people came out and said the standard model is complete. That was a moment that has created a decade of crisis. That statement. And I want to put a question mark there. Is the standard model really complete because you've discovered the last particle? And part of the answer I want to give is not at all. The standard model isn't just a bunch of particles. If you have a bunch of particles on their own, in a free theory, no interactions, you do not have the world we have around us. Just as critical as this list of particles is this t-shirt. If you go and visit CERN, you can buy the t-shirt. Sort of really comes from a scribble on a blackboard by John Ellis. It's not to condense down what the standard model is. And what this really is telling you is all the interaction. So some of you will have had courses on field theory. This is photon propagation and its interaction of gauge bosons with each other. This is the term where fermions propagate and where they interact with gauge bosons. And all of that is the successful bit of the standard model that's been tested over decades. It's the repetition of cues over and over again in more sophisticated ways. Part of the reason the discovery of the Higgs boson was important is not because it was the last particle. It's because it opened the window, opened the door to studying more than half of this t-shirt. And really here, we're still only just starting. Many of the fundamental questions that lie in this thing here, this is in all textbooks. But just because it's in a textbook doesn't mean it's physics. It's written down in all textbooks. But our job as physicists is to establish that that's what nature does. And this is only just starting to get going. And these interactions, we're going to sort of talk through some of them, are unlike any of the interactions we've looked at before. Now, I should say this talk is adapted from a Nature Perspectives article, the Higgs boson turns 10. Some of what I say you can find in more detail there. Some of what I say is sort of more recent thinking than what is in that article. But that's a good place to start if you want to see a written version of what I'm saying today. So, first thing, just to remind ourselves, take a magnetic field. We know fields well, electromagnetic fields are the most common ones we deal with. They have a source, and then you produce a field, like the Earth's magnetic field. And you can go and measure that magnetic field, and we have ways of altering that field. That's sort of what we take for granted in QED. Well, there's another field all around us, and it's the Higgs field. We don't notice it in the same way you don't notice the magnetic field around us, unless you've got a compass, unless you've got the right instrument for going to measure. Well, the right instrument for going to measure the Higgs field is a little bit bigger than a compass, a little bit more expensive than a compass. But the whole point of the Higgs boson is that we're able to study this Higgs field. So what is a Higgs boson? Essentially, it's an excitation of the Higgs field. It's a local excitation of the Higgs field. And that's what the Large Hadron Collider enables us to do. It enables us to actually touch that Higgs field strongly enough that we excite it. Now, there's a hypothesis at the standard model. It is important that we still call it a hypothesis. But fundamental particles get their mass from interaction with the Higgs field. Now, the Higgs field was in the whole Higgs mechanism was invented in a particle physics context in order to give masses to gauge bosons. But actually, there's a very important term for Lagrangian, which is a fermion field and a Higgs field with some number, Yij, called a Yukawa coupling. that gives mass also to all the fermions. So not just to the W and Z bosons, but supposedly also to all the quarks and the leptons. Neutrinos are a bit fuzzy, so I'll not talk about neutrinos in this context today. First, look at the list of particles, the charged particles of the Standard Model. And let's look at the knot as shown here. So let's put them on a vertical scale, a logarithmic scale, showing their range of masses, from the electron down here, all the way up to the top quark. The top quark is 100,000 times, 300,000 times heavier than the electron. There's a big difference. It's a big mystery of why these particles have such different masses. And the textbook answer is that the heavier particles, at the top quark here, interact more strongly with the Higgs field than the lighter particles. Here, a peak quark. You see it's leaving less of a trace in its animation of the Higgs field. So that's the fundamental premise, that all of this wide range of particle masses comes about because there's a wide range of interactions with the Higgs field. So is this true? Well, how do we actually discover a Higgs boson? One way to discover it is you collide two gluons, and the gluons produce a top and an anti-top quark pair, and that excites the Higgs field. And then maybe the top and anti-top decay, and just leave that excitation of the Higgs field there. That's the Higgs boson. And for quite a long lifetime. And then at some point, that a Higgs excitation can itself decay, in this case producing a top and an anti-top quark, which then don't quite have enough energy to sort of fly out, and they annihilate, and in this case produce two codons. So that's one of the easiest ways of producing and seeing a Higgs boson. And the characteristic signal that you see experimentally is that you take every event that has two photons, you look at the invariant matter of the pair of the photons, you count how many events have got an invariant mass of 105 GeV, 106 GeV, 107 GeV, and so forth, and you find that there's a tiny little bump here. That tiny little bump is in excess because of this one way of producing two photons through the Higgs. And because the Higgs has a definite mass, you get that bump in a particular place. That's one of the ways the Higgs boson was discovered. But indirectly, it also tells us that, or allows us to check whether this hypothesis that the Higgs is interacting with the top quark, or the Higgs field is interacting with the top quark, is true. You can check the rate of events. You can calculate the rate of events that you expect from this. And you can see if the number of this little excess here is consistent with that rate of events. And what you get is something that is consistent to within 10%, which is the measurement accuracy. So that's a good sign that we're on the right track and that maybe the top quark does interact with the Higgs boson. So we're trying to establish, does the top quark get its mass from the interaction with the Higgs field? And this is telling us it's at least consistent. The problem is you don't see that top quark. I can show you an animation with the top quark there, but you don't really know. So how can you be sure it's top quark in those intermediate stages? Or how can you establish in some other way that the top quark is getting its mass from the interaction with the Higgs field? So some of my colleagues say, we don't care, direct, indirect, everything we do is indirect. When you build a detector, you measure electrical signals. You're not directly seeing the photons, you're not directly seeing the Higgs boson, everything you do is indirect. But I think there's a qualitative difference, and I want to take us on a little detour. First, through a children's story from Le Petit Prince, The Little Prince. So this is a 6-year-old kid, starts off with the book, 6-year-old kid who's read a book about boa constrictors in the jungle and how they swallow their prey whole. And so he does a drawing and shows it proudly to all the adults around him and asks, does it scare you? And the adults say, well, why should we be scared by a hat? So the kid understands that the adults are a bit slow, they need a bit more help, and he does a second drawing and says, well, my drawing wasn't a hat, it was a boa constrictor that is sort of an elephant. This is indirect evidence. That's direct. And that one is direct. There is a difference. It's also nice to look at other fields of physics where this difference has been emphasized or brought to the fore. And one of them is gravitational waves. So Halves and Taylor discovered a new type of pulsar and got a Nobel Prize for it. And why did they get the Nobel Prize? Because the orbital period of that pulsar changed slowly, about 75 millionths of a second per year. And they were able to measure that because the system was emitting gravitational waves. So they got a Nobel Prize for the indirect observation of gravitational waves. And a couple of decades later, another Nobel Prize was awarded for the direct observation of gravitational waves. And you probably all know the story of LIGO, having seen this direct observation of gravitational waves. It's an extremely impressive measure. So is there a direct way in particle physics of seeing that at least some of the particles, some of the fermions, the particles of the kind we're made of, get their mass from the interaction of the Higgs field? Well, there is another way. You can collide two gluons again. You can produce two top forms. And sometimes you have enough energy that a Higgs comes out with it. That excitation comes out with it. Well, okay. So in principle, you can do it. You can see how often the Higgs excitation comes along with two top forms. But the question is, can you observe it? And particle physicists have a convention of what they call observation. So this is an illustration here of statistical significance. Many of you will have seen this in statistics courses, maybe taught differently from the way particle physicists do it. The question is, how can you be sure you're seeing a genuine signal? So this is a signal. I put a background here. I've put a signal on it with some number of events and done a fit. And the blue line and band is the fit. And what we can do is gradually increase the data. So the band is the uncertainty on it. So you see it's pretty consistent with 0. You can increase the data a bit. It's now pretty consistent with a negative signal. And jumped around. You can increase the data a bit. You increase the data, the significance has gone down. 1.3 signal is now 0.9. And you do that for a bit longer. And then as you increase the data, the amount of data, slowly it hits 3 sigma, which is the convention in particle physics for evidence. You're not expecting it, don't be surprised if it goes away with more time. There have been probably dozens of 3 sigma things that have gone away with time. You're looking at so many things in particle physics, but some are bound to fluctuate up. And typically they're not there. And you can increase the data further. And what's considered the gold standard is 5 sigma, ideally with 2 independent experiments. We've also had things that were 5 sigma and disappeared. Okay, so that's great. So what was the situation at the start of the LHC? When the LHC was built, it was designed so that it would find the Higgs boson. And that was it. That was the one guaranteed period. But when people looked at these other channels to see, could we find direct evidence for the Higgs interacting with top groups, the Higgs interacting with peak groups? This was the statement that you found in the articles. this is sort of quoted from this article, which was looking at both of those studies, but basically this was what was in the long technical design reports for Higgs physics. It was considered just hopeless. But people have thought hard in the meantime. They've thought hard. The experiment is designed better than expected, or better than hoped for initially. They were hoped to perform very well, but they did even better. The accelerator delivered lots of data. It's really worked very nicely. And today, this is where we stand. So this is the indirect process, where you have 1 in 2 billion events that have a Higgs. And if you look at the events with the top quark, and you plot the invariant mass of the 2 photons, and you have 2 photons, you find a bump. 1 in 2,000 events with the top quark have a pair of photons with the mass that is consistent with the Higgs. So you're much more likely to find a Higgs boson in events with a top quark present than in events where you don't explicitly see a top quark. And that's telling you that top quark is interacting with the Higgs field. That is not considered to be possible. So that's gone from indirect evidence to direct observation, essentially in the space of, that happened in the space of 6 years. Compared gravitational waves, where it took decades. So if you hear somebody tell you that the Large Hadron Collider has not seen anything or done anything since discovering the Higgs boson, well, it's gone and essentially done the work of the second Nobel Prize. Only nobody said it. We can discuss offline why, but that's the significance of what's happened. Well, that's the top quark. People thought it wasn't possible to demonstrate the origin of the mass of the top quark. It's been done. People thought it wasn't possible to demonstrate the origin of the mass of the peak quark. It turns out that's been done as well. In this case, by observing the Higgs decaying to BB bar. And the tau, well, people thought that might be possible. And, well, it was possible, and they've done it by observing Higgs decaying. So these particles are the 3rd generation. And it's really quite a remarkable achievement that the LHC has observed, has essentially established the origin of mass for the whole of the 3rd generation of large particles. Not neutrinos, but the massive particles. This is really quite remarkable. Okay, so where do we go from here? Well, this plot here shows the masses of the particle on this axis, the strength of the interaction with the Higgs field on this axis, normalized slightly differently for the W and Z than for the quarks and the leptons. And the real question now, given that these particles come in generations, is do the other generations also get their masses? Because these generations got quite different masses. It's a puzzle. And one explanation of that puzzle is there's some other mechanism that affects the mass differently for different generations. So the real question, the sort of most imminent question that arises is, can we discover the origin of the mass? Can we? I'm a theorist. I'm not doing any of this. I'm just telling the story. So what should we be saying about this? There's actually quite a lot of things. One is this discovery of the origin of the mass of these heavy particles. Another one is that we really take a step back and pretend to be science fiction novels. Always, there's no harm for a while in pretending to be a science fiction. A field is something you can control. Mass particles get their masses from interacting with that field. So, if you can control a field and the particles get their masses, maybe particle masses are not fixed. We're used to thinking of the electron mass as a fixed thing. Okay, you can build a solid, then the electron behaves as if it's got a different mass. But the real electron mass is fixed. But the masses of elementary particles be controlled and modified. Well, that is science fiction, but keep it at the back of your minds. Yet another thing, you may have heard of people talking about fifth force experiments. Well, the people designing experiments to search for fifth forces are really behind the curve. Because the Higgs is, in interacting with the two different fermions, is a fifth force. So they've got the classic signature. If you could not actually modify, if you could go and measure the force between two particles, you would see that it behaves exactly like a fifth force, with a very, very short interaction distance, which is of the order 1 over the Higgs mass. So that's another respect in which this is actually quite a significant thing. And actually, people are sort of trying to see it. They haven't quite phrased it this way, but they look at the production of top quarks and see if the production of top quarks is altered by the Higgs field. And, well, it's a difficult measurement, but that is essentially a measurement of the Higgs interaction as a fifth force. So this is important. Oh, so that's great. That's the heavy particles. And for a long time, particle physics has gone in the direction of heavier, heavier, heavier. Why we build bigger accelerators, bigger experiments. But I told you that we've established the origin of the mass. Again, the experiments have established the origin of the mass of the heaviest particles. And now they're moving towards the moon. They're moving back down. And it's useful to think of why is the mass of the particles we're made of actually important? Because if it's important, we want to know where it comes from. So these are the particles we're made of, the electron, the up, and the down quark. There's some gluons going in with the two photons going in. But basically, let's concentrate on the matter particles, the fermions. And an atom is, for example, a proton and a neutron, an electron, up quarks and down quarks, and so forth. So let's start with the electron. So what's the radius of an atom? This is basic quantum mechanics. The Bohr radius of an atom is h bar over the mass of the electron and alpha, and then c is the dimension of the electron. So the radius of an atom is proportional to the inverse mass. And in the hypothesis that the mass comes from the interaction of the Higgs field, it's proportional to 1 over this Yukawa interaction of the strength of the electron's interaction with the Higgs field. And if you change the mass, this video comes from CERN, if you somehow that interaction were to reduce or if the Higgs field were to turn off, the universe would suddenly fall apart. All the atoms would fall. So the mass of the electron is a pretty important thing. It'd be nice to know where it comes from. How about the proton? Well, the proton is a funny thing. Take the mass of an up quark, a second up quark, and a down quark. That's 2 MeV, 2 MeV, and about 5 MeV. When you add them up, you get 9 MeV, and the mass of a proton is 900 MeV. So there's a lot of physics happening in this electromagnetic and strong interaction. The mass of the proton does not come from the masses of the up and down quarks. But there is a difference between protons and neutrons that is important. Let's highlight it here. But the neutron has a down quark where the proton has an up quark. The down quark is a little bit heavier, and that makes the proton a little bit heavier. The electromagnetic part is also different. So it's a delicate calculation. But this is important. We'll come back to that in a second. This is important. The fact that protons are lighter than neutrons means that neutrons dictate protons, not the other way around. That's what makes protons stable. And again, that's very important for the world around us, because if protons were unstable, we'd have no hydrogen. Maybe you'd have nuclear physics bring together things and make them stable, in the same way that a deuterium is stable even though the neutron is not. So you might still have complex nuclei, but it would certainly be an extremely different world. So again, chemistry, biology as we know it. It's thanks to the masses of these particles, which are supposedly coming from the interaction with the Higgs. But we don't know that for a fact. Now, this back of the envelope calculation is very dodgy. When somebody tells you, look, add up these 9 MeV and it accounts for the difference on something that is 100 times heavier, you have to be a little bit suspicious. But luckily, our colleagues who calculate quantum thermodynamics on the lattice have done this study. And what they've done is they've worked out how much the up and down mass difference contributes to the total mass difference between the proton and neutron. So the contribution to GUD, the neutron is not charged, the proton is, so that makes the proton heavier. But the difference coming from the up and down quark masses outweighs that. And you get this small effect. This is the true difference, and that's their calculation. It's not 5 sigma. It'd be nice to have that done better, for sure. But basically, the evidence points reasonably convincingly that it's up and down quark mass being the reason why neutrons are heavier than protons, why protons are safe. This is all the textbooks. Every single particle physics textbook you pick up is going to tell you that this is what it is. But you have to be careful whether what is written in textbooks is actually what is in nature. That's our job, or your job, over the coming decades. So do all of these other particles actually acquire their mass in the same way? Gavin mentioned the European strategy. That's an ongoing process across Europe, spanning about 2 years, to try and work out what we should do next in particle physics. Next, we should develop a visionary and concrete plan that greatly advances knowledge in particle physics. Do a next flagship collider at CERN, and to identify alternative options if that's not possible. So what are the rough scenarios that are possible? Well, one thing is already approved, it's part of comes from the previous strategies, which is to increase the rate of collisions at the Large Hadron Collider by a factor of 10. And that's approved. We are creating under construction. Maybe even some of you sitting in the room are constructing it. Options on the table for the future include something called the Future Circular Collider as a E plus E minus collider. So it's electron-positron collisions at quite a wide span of energies from 91 to 365 GeV. Well, 91 has been done before, after about 200 has been done before, but this comes with 300,000 times more collisions. That is a huge difference. We'll come back to that again in a second. And there are alternatives. China has a project that is similar. There are also linear colliders rather than the circular one here that have been proposed. And there are differing opinions about the relative merits. I'm in favor of the circular one because you can put many experiments. Many experiments means you can, if one gets a funny result, you've got an option to cross-check. You've spent several billion euros. You don't want to be relying on just a single thing which might go wrong. There's also a possibility of a future proton collider, which would have an energy center of mass energy that is about 7 times larger than the others, and would also have 10 times more collisions than the high luminosity atoms. And again, there are alternative proposals. For example, China has a super proton-proton rider proposal, and there's also the idea that's come up in recent years of a muon collider. And I understand Michelangelo Magno is going to talk to you in perhaps slightly different audience in a few weeks, and he's done some interesting studies comparing the muon collider to the FCC hadron collider. So we can tell you more about that. So what's the next major step? The next one is really establishing if for the first of the second generation particles that we can access at the LHC, whether it acquires its mass in the same way. There are first indications, the 3 sigma sort of level, but not yet 5 sigma. So that's one major goal, to really sort of breach that second generation. The chunk walk is tough. You can almost certainly get it at any of the E plus or minus 4, not almost. You can definitely get it at any of the E plus or minus colliders, being proposed in the future. At the LHC, it was long considered impossible, but we've seen that things that were long considered impossible sometimes become possible. And there's a question of whether the LHC experiments can just get there. For the time being, I'm a little bit skeptical, but I would be delighted to be proven wrong. What about the electric? Well, let's start with the strange port. The end of the second generation. That's becoming clear. It might just barely be at the edge, at least some of the best of the future circular colliders in plus and minus mode. It's tough. The electron would really be important. I mean, that's another Nobel Prize that deserves to be won, if it can be. Discovering where the electron gets its mass from is really, we're getting the story then of what we're in. And why the world that we see around us is the way it is. But that's pretty tough. At the moment, no one really knows how to get there all the way. People are inching closer. They've got ideas that can get close to it, but not 5 sigma within. But again, over the space of decades, what is not 5 sigma today might well become 5 sigma. And that's the job for those who go into particle physics today, of figuring out how to take these things that are considered difficult, almost impossible, and making them possible. Okay, so I told you about some things that are not quite possible, not guaranteed. When you think about the desirable features of a new high-energy physics project, well, there's quite a few desirable features. And one of them that sometimes people talk about is an important target to be reached, a guaranteed discovery. Sometimes people call it the no-lose theorem. And when in an earlier variant of this talk, I called it the no-lose theorem, people said, don't talk about losing, talk about winning. So it's now a guaranteed discovery. So all this happening around us in the standard model of movement characteristics only happens if the Higgs field is non-zero. Why is it non-zero? If we think of all the other fields that we know around us, classically, if you don't have a source, you don't have a field. No Earth, no magnet inside the Earth, no magnetic field. What's special about the Higgs field is you don't need a source. It's just on. There, it's a non-zero Higgs field without any source at all. That's the thing that makes the Higgs field so very different. Well, there are a few things, but in basic things, you really get down to the root of it. That is the thing that makes the Higgs field so very different from all the other things. And in a sense, the fact that it's non-zero, which I call V of phi, and I'll explain that in a second, is really the keystone that holds together its whole edges. So the answer is a potential. Well, no potential, that's high school physics. You have a potential, you let the ball roll, it rolls to the bottom. Fine. That's a potential. The slightly different thing about it, so this is a drawing of the Higgs potential. What people think is the Higgs potential. The different thing is that this is a potential density. This is the potential at every point in space. If you write a little volume of space, and you take the Higgs away, that volume of space can be associated with an energy. And you take the sort of Higgs field to value this differently, it will be associated with a different amount of energy in that little volume of space. And people write this, they write a dimensionless, essentially, they write phi squared minus phi squared plus phi to the fourth. I left the equation out on this slide because this was talk was adapted for a different from a talk for a different audience, which would not have wanted to see equations. I should have written it back on. But let's just work out what the depth of that potential is, or state it though. So in the units the particle physics use, GeV per Fermi cubed, it's about 10 to the 10 GeV per Fermi cubed. That's quite a big number. You think of a proton, that's about 1 GeV per Fermi cubed. That's the order of magnitude. It's about 10 to the 10 times larger than the proton is. 10 billion times larger. If you do the numbers more exactly, it's about 40 billion times nuclear density. Or if you put it into units, everyday units, that's, well, I'm not sure that's very helpful. 10 to the 28 kilos per meter cubed. It's hard to imagine. So how do you go about imagining that? Well, okay. You can more or less imagine the Earth. What its mass means, it's hard to imagine, but at least you can imagine the Earth. And let's put that the Earth at neutron star density, sort of polar neutron star. It sounds familiar. Okay, so you do that. You transport it to Lisbon, and you rest it on top of the Estadio da Luz, and that's the Earth at neutron star density. It's quite impressive. Okay, I mean, you need some quite impressive engineering if you want to stay up. That's another matter. What about the density, the energy density associated with this depth of the Higgs potential? Well, you take the Earth again, and you fit it into a glass. That's what we're talking about when we're talking about the Higgs. So if anyone tells you, oh, astronomy is so much better, well, astronomy is wonderful. But if you want to know where the largest energy density is, that's neutron stars, that's astronomy. This is what particle physics is trying to prove. Not a competition, they're both wonderful things. But we shouldn't forget that particle physics is doing something that is truly quite amazing in terms of what it's trying to probe. So how do you probe that? Well, this potential is not a perfect harmonic potential. And anytime you have a non-harmonic potential that is not harmonic, you can have communication in different modes, different excitations. And in particular, you can go from a mode that is a single Higgs boson into a mode that is two Higgs bosons. And by measuring the rate of that, you can see just how anharmonic it is. You get the third derivative of that potential. Well, that's not easy to do. Just to give a sense, suppose we know the second derivative, that's the mass. We know the first derivative is 0 because we're the minimum. Let's suppose the fourth and higher derivatives are fixed and just see what kind of constraint we can get on the third derivative and how that affects the potential. So this, roughly speaking, is what we know today. With the current limit of lambda 3, this third derivative. By the end of the LHC, we know it somewhat better, but that is still not even really with a proper 5 sigma observation of this process. It's just sort of a constraint coming from not quite seeing this process of producing two Higgs bosons. You get an indirect constraint from a lepton collider if you build it, but really where you get this knowledge to start to be more solid is if you build a future hadron collider. You get this knowledge of this cubic coupling to within a few percent. And this direct activation of Higgs, the two Higgs bosons, is, I think, something we should consider to be a guaranteed discovery. If we build a machine, we build that machine, there is a discovery in there, which is really Higgs turning into two Higgs bosons, which is the really strong direct evidence for this potential. Again, let's take a step back and do some science fiction. Maybe you discover that it's not that potential. Maybe you discover that there's a second minimum. Now, there's a second minimum like this in the simple potential. You're just going to tunnel right. And anytime you end up in that state, you're just going to tunnel right through in no time at all. So you can't do much of it. So you need a couple of ifs. You need to say, well, suppose this was potentially different, there's another minimum, and there's some reason why you can't tunnel through, maybe some topological reason. Then you could imagine creating bubbles in which matter will be totally different, assuming matter that we know of gets its mass from its negative, which we also haven't demonstrated. So this is all science fiction, but we know so little about this that we can't rule it out. In a sense, in terms of the mission of particle physics, it would almost be reckless not to at least try and establish as much of this picture as we can and see what it really is, not just what's written on paper and textbooks. So I've got a few minutes left. What I've told you is about essentially the story of the guarantees. But it's important also that we explore into the unknown. That's also part of the goal of particle physics. And that's a bit of particle physics that has sort of been challenged over recent years, because we've not found anything beyond these aspects of the standard model. We've been good. There's a list of things we like: dark matter candidates, explanation for the thermal masses. It's not just the Higgs mechanism, matter-antimatter asymmetry, an axiom to solve the strong CP problem, the fine-tuning of the vector weak scale, the fine-tuning of the cosmological constant. There's a lot we want. The problem is we don't necessarily know where these things sit. That's the difficulty. And there's always a temptation to say, well, my experiment is going to search for dark matter. It might even find dark matter and get excited about it. But if you take the example of dark matter, this is from the SNOWMASS report, which is the US equivalent of the European strategy, planning their future in particle physics. This is the range of masses for different kinds of dark matter. This is the range of interactions for different dark matter candidates. And you can't really read the scale, perhaps, if you're sitting at the back. There's about 30 orders of magnitude here. And there's a lot of orders of magnitude here. I mean, it goes all the way up to magnitude, the Planck. So if you're sitting in a little corner of this, which is what a lot of dark matter search experiments do, you may get lucky. But you have to be careful about promising statements like the LHC will discover, or any experiment saying that it will discover. It's a risky statement. We can say we will explore. And we can argue that we're exploring in a well-motivated region. Maybe the MSSM or the NMSSM are well-motivated. But we have to be careful about what we promise. What we can promise is how well we explore, not how well we will discover. Now, the Higgs is pretty central to all of this. And this is sort of written on the back of a napkin, essentially, by Jan Judice, who's the head of the theory department at CERN, for Fabiola Gianotti, who is the director general of CERN. Let's just typeset that for them. This is the part of the Lagrangian associated with the Higgs. And the point that was being made by Jan Judice on the back of the napkin is that every single bit of this Lagrangian is somehow connected with mysteries. This Yukawa interaction, origin particle masses, it's a mystery. Even if we discover that's where they get their masses from, why do you have such a wide range of value of Yukawa interactions? So that's this thing here. Stability. Is there one minimum? Are there two minimum? Is the universe stable? Could there be a lower minimum? That's a pretty important question too. The cosmological constant. I sort of blindly say you've got the density of the Earth in the glass. So why doesn't that affect us? We think it should affect us. And that's the mystery of the cosmological constant. Why is the cosmological constant so much smaller than this density? And then you've got naturalness, which is a harder one to explain. But basically, the vacuum fluctuates. Quantum fluctuations of the vacuum alter its properties. And when people do quantum fluctuation calculations with the Higgs boson, they don't understand why the Higgs boson is as light as it is, approaching the Planck mass. And that's a mystery too. So there's a sense that looking at things to do with the Higgs boson is also one of the dimensions of our exploration. albeit in a somewhat indirect way. And for example, this is a plot taken from one of the linear collider projections, showing that you can measure a range of things and get a fingerprint that might point to a specific model. This one is called the 2 Higgs doublet model, saying the field is more complicated than just the Higgs anomaly. And that's a powerful thing to do. Indirect is valuable. And typically what you're doing when you're probing indirectly is you're looking at a coupling strength or a deviation from the standard model and a mass scale of new physics. And you're trying to, well, the exact relation depends on the type of new physics, but you're trying to push this line further by going higher to higher energies, essentially, or higher accuracies. So are you exploring? The critical question is, when you build a new collider, will you explore sufficiently far? And the increase in precision at a future collider such as the XCCEE, if you look at it across a range of different observables, so these blue bands, the dark blue bands are today's expected increase in precision, both the logarithmic scale. And you see that you've got an increase in precision that is not bad. The light blue is what you could do if you manage to get rid of the systematic errors that people have estimated. So there's a lot for people to think about to improve. You'd be probing quite high scales. And the number that I like to extract from that is the geometric average across all of these. It's about a factor of 20 in precision. And a factor of 20 in precision, when you work out how these things work, you take the square root of it to work out what kind of increase in energy reach you're effectively getting during their sensitivity physics. So making that better, part of a fun exercise for particle physicists in terms of making this exploration more powerful. If you don't find anything, you've not lost. What you've done is you've built the foundations of the future of the field. Today's field relies extremely heavily on what LEP did. LEP did not find any new physics. But without the results from LEP, we would be nowhere near achieving what we would. What about direct evidence? Well, what does direct evidence look like? I showed you the direct evidence for the Higgs boson. The bump. That's the best kind of direct evidence. It's not the only kind, but it's the best one. And these are various hypotheses of new signals showing the bumps that you might see. This is at Atlas. And again, you can ask, what improvement would you get with a future collider? And it's nice to put, I said a factor of 4 or 5 before in the context of indirect evidence. How do you judge, is factor of 4 or 5 good or not good? Well, let's take a simple standard candle. I like the Z prime search. It's the simplest search, where you look for a resonance referring to a pair of electrons, like a positron, neuron pair. And at the tevatron, their exclusion limit, if they carried on running until the end, analyzing all their data, would have been about 1.2 T. At the LHC, by the end of its run, it'll be about 6.7 T, so a factor of about 5.5. So that's that's the amount of exploration you get, state of the art, across, roughly speaking, 30 years, 30, 40 years. So what would you get from a future circular collider in the Hadron mode? Well, roughly speaking, you get a factor of 6.1. So then you take this exclusion limit of 6.7 up to about 40 T. So the plans that particle physicists are talking about are trying to make a step forward that is of the same order of magnitude as the step forward that people have taken over past years. That's keeping the same level of ambition in terms of the physics exploration that we're trying to do across hundreds of channels. And this is just a subset of all the different searches that happen up here. It's really quite impressive how many different types of signatures the LHC is looking at. It's a truly multi-purpose machine, And this is just research. The LHC is doing a huge number of other things, including heavy ion physics, which is one of the specialities in the theory group here. It's really a vast range of things being done at the LHC. So that brings me to the end of it. Particle physics hasn't stayed still after the results of this one. It's done some quite impressive things in a relatively short amount of time. And going forward, there really is a guaranteed discovery that I think particle physics should be aiming for, which is the observation of the production of two Higgs bosons at the same time. Clearly, by multiple, not just by more than one experiment, reasonable precision. We really want to get there, because that gets to the bottom of why this field around us, but it's really mysterious. It's so subject to energy density that we don't see. But there's a big mystery sitting there. Why this field around us is non-zero. So there's a guaranteed discovery. And there's also a step up in exploration, factor of 4, 5, 6, which is really what we should be aiming for. That will be delivered by these future experiments with diversity and robustness built in. So that's what particle physicists, in my view, have achieved and are trying to achieve in the future. Thank you.